Technology. All right. So, this talk was for a brief time called Working with Riemann, and I thought nothing of it because the gays have taken this stance to heart. However, it might be somewhat problematic for me as a white person in a room full of white people in Portland, a very liberal utopia founded essentially on nation-scale white flight, to reenact this dance. So, we'll be cognizant and respectful of that. This talk is called Working with Riemann, and I want to take you on a brief tour of all the wonderful things that my terrible part-time project can do to your infrastructure. A while ago, I was an operations engineer, back-end engineer, and I was responsible for the care and feeding of this large distributed system with many moving parts, some of which were unhappy, but I didn't know which ones. I had a problem with visibility. I couldn't see things, right? We're working with invisible sky gods, and like, what are you going to do? So the system and its predecessors that I built were intended to make the invisible real, to make it tangible in a way that we can interact with. So Riemann accepts information from all these different services and combines it, unifies it, and shows it to you in a dashboard. And then it can push that information out into other analysis systems, maybe Graphite, PagerDuty, Influx, Librado. What kind of information am I talking about? Well, we're talking about events. Meet an event. Our happy little event here, she is freshly arrived from a Riemann stack, and she is identified in space by two coordinates. There's a physical coordinate, like a host, and then there's a sort of logical coordinate, like a service. So a host might be a DNS name, like api3.tx, and maybe a service is disk space on /foo, free megabytes or something. So these could be complex, but they're essentially discrete. There's a continuous variable. We need to take that event in its sort of host and service plane and pull it up, extrude it into 3 dimensions. This will be the temporal extent of the event. So an event is uniquely identified by its host, API33, by its service, HTTP 99th percentile latency, and then by a time and a TTL that determines the duration for which that event is valid. And at those coordinates, there will be some values. Maybe the state of the service is warning. Maybe it's got a numeric metric like 0.337. Maybe it's got some description of an error that occurred or a stack trace. So events in Riemann are represented as maps of keys to values. Those 3 keys comprise the primary key, host, service, and time. You uniquely identify the thing we're talking about. And then things like TTL, the state, the metric, the description, maybe some tags, maybe other keys and values can be added to give us context and information about what it was that thing did. So these events flow into Riemann over TCP, and then they arrive in this gush, this roar of events flooding into the system, and we have to do something. What do you do with that stream? Well, the first thing I do whenever I go to a creek is I pull out a bunch of rocks and I toss them into the creek and start making dams and waterways and so forth. And I was thinking about this as an operations engineer who was also 6 years old. And it's amazing how that works. I haven't aged at all. So you can build in barriers and filters. So this might be like a filter that only lets through events where they match some shape or where they fit certain criteria. Maybe all the API requests, the number of requests per second, those are the ones that come through. And then we could take those requests, maybe they're really heavy if they've got a big metric and light if they've got a small metric, and we can put them into a water wheel. And that water wheel is going to turn faster the heavier the events are and the more events come through it. So that spinning of the water wheel can tell us something about the flux, the rate of events, the rate of requests per second. And we can take those rate events and they'll float along down the little channel we built. And we can drop them off into a conveyor belt and they'll whir, and then we can stamp them down with an industrial compressor to some more manageable form. Load them into a little rocket, add some struts, and fire off the engines there. And the impact on planet graphite, and this is monitoring with Riemann. So that little diagram I drew for you, that's like the physical intuition I have for stream processing. I hope you share it. So we have streams, we gated them with where, we took a rate of the events flowing through, and we pumped them off to Graphite. Okay, so let's put some parentheses around that, because I like Lisp. I'm a McCarthyist. Now let's drop the pictures so this is a little clearer. Okay, does this look at all like a maybe a tree, or maybe like an XML document, except we got rid of all the cruft? That's right, you're using S expressions right now. This is an old and beautiful technology from a more civilized era, given to us by the great papers of List 1 manual. So streams feeds to where, feeds to rate, feeds to graphite, and we'll add some arguments. So the where filter, it needs to know what to act on. So we're going to filter where the service is requests. And then we're going to take a rate every 5 seconds, and then we'll send that to graphite. And now Lisp interprets a list, wrapped in parentheses. The first thing is going to be a function. So here we're calling the rate function, we're passing it the argument 5, and we're giving it 2 child streams, graphite and maybe InfluxDB. So in general, Riemann streams all have this form. They're going to take the name of the stream, some optional arguments that control how it behaves, and then some children to forward onto. And this stream, when it gets invoked as a function, it collapses up, becomes a new stream, which we can pass to something else and something else. And that's how you can build up these complex topographies. Everything is uniform. They compose as functions. So, what kind of functions? Well, we can filter based on regular expressions. We can do mathematical operations, like filtering where the metric is between 2 and 5. We can filter everything tagged cat. And because these are just closure programs, Lisp programs, we can say, okay, where all 3 of these criteria hold, where the state is not okay, where the service is foo, and where the host is anything.tx. We can also alter events. So I can say, when I graph this, set the host to be nil. Or, if there's a missing TTL, fill in a default value of 60 seconds. Or, change the service, adjust it, using the stir function and tacking on the string rate. And then we'll pass that to this rate of 5 and graph it. So this will call the stir function with the current service in the event, and then that string rate, which means we're going to turn an event that has a service foo into an event with the service foo rate. We could also scale things. If I've got kilobytes and I want to go to megabytes, I'll scale by a factor of 1 over 1024. Or maybe in generality, I could perform a streaming map operation with some arbitrary function of an event. Or I've got a function that makes events sad instead of happy, and I'll pass my events into this S map with Sadtron 2000, and they'll pop out sort of something a little less idealistic about the world. This is a metaphor for operations engineering. Mapcat obviously just maps into catmates, so you get to emit lists of events, and each one that we pass to return. We could generalize all the way to streaming reductions, where you get to keep the previous event around and combine them. And if you've got a streaming reduction, you could do differentials. So I could compute the difference between every pair of metrics. So if I've got something that reports like a rising counter and I want to know the rate per second, I could do a differential in time to extract those information. Or I could compute a rate, as we already saw, it's where I sum up the metrics over a given time interval and then divide by the time period. Really useful for things like request counts. Or I could do a counter, that's an integral. So I'm going to take, okay, I did one event, I did one thing, and then I'll sum them together over time. We can smooth and filter those numbers too. So if I wanted to pass on only differences, I could use a change stream. And I'll give it some function that extracts a value from an event. And it's going to pass on events only when that function's value changes. State is a function, so I can say, hey, when the state of an event changes, then let it through. Or I could do a smoothing operation, like take a half-life, an exponentially weighted moving average with a half-life of 10 seconds, and graph that. I can eliminate flapping services with a stable stream. Say I want to emit things only after they've had the same value for 60 seconds. So this way I can suppress transient interruptions. Like when I do a restart of a process, it's normal for its request rate to drop to 0 for a couple seconds and then come back up. But if it dropped to 0 for a minute, I would be unhappy. We can do flow control. You could throttle, say, give me only 4 events every hour, and we'll drop anything that comes in after that point. Or I could do a roll-up. Maybe I want to get emails immediately about events, but I only want to get like 3 emails per day, or 3 emails per hour. And so after those first 3 emails, it'll batch everything up and wait, and then send me one at the end of the hour, giving me a summary of everything that happened. And I can batch things. Oftentimes you're interacting with an API that accepts requests that can have multiple constituent parts. So I want to fire off a request to InfluxDB containing 55 or 100 events, but I don't want to impose too high of a latency cost. So I'll say every 1 second or every 100 events, whichever comes first, fire off this batch. And with those batches, I can do things asynchronously. If I say async queue, this is a stream that defines a new thread pool worker, and then I can give it, say, 10 threads. And everything that hits that stream returns immediately. It pops into a queue, and then some other executives take care of it. So I can trade off between wanting synchronous behavior, wanting asynchronous behavior in the same streaming language. We can do analyses. Taking percentiles. Every 10 seconds, give me the minimum, median, and 99th percentile latency. I can compute clock speed between nodes. Super useful. You all think you run NTP. I'm betting about 10% of you don't do it right. And I say this purely because every week someone on the Riemann IRC channel shows up and is like, hey, I'm getting this weird behavior with my graphs. They're going backwards in time. It's like, oh, are your clocks synchronized? No, they're not. This happens to me a lot too, actually. It's really hard to run correctly. We can do apdex metrics. This is one of my favorites for high-level observability. You take your requests and you segment them. You say some are okay, some are, I'm all right with that, but it's not great, and some are really terrible. Apdex is the fraction that's okay plus half of the fraction that are okay, acceptable. And we can combine those events across time too. So I could say, give me a moving time window. Every time an event comes through, don't give me just that one event. Give me the last 100 seconds. And then the next event, give me the last 100 seconds. And so you'll stamp your way through time, 100-second intervals at a time. And then we'll map that, taking the minimum event from the last 100-second window. Or we could compute fixed windows, where it's, instead of progressively overlapping, we have a solid chunk, and then another chunk that's completely discrete. So these obviously have different performance characteristics, and also different observables. You'll get various behavior out of them. We can combine not just across time, but across space. So let's say that I have free and used disk space coming into the same stream, and I wanted to compare them. In order to act on them in the same place, I need a stream like project that will seize them and bind them together. So it says, give me every pair of services, one is free and one is used, and then we'll map those with the sum folds, add them together, call that total, and graph it. So project is going to have a little box for the last used event, and a little box for the last free event. And every time a new one comes in, it displaces the old one, and we get the pair, and we can act on the two in conjunction. And we can generalize that to coalesce, which says, give me all of space-time. You know, show me like everything that's happening across the entire world, every host and service uniquely. What's the most recent thing you know about it? And we can use that to find out what's the median latency across the entire cluster, or how much disk space am I using across all services. So coalesce is going to have this sort of plain little slots for each host and service. As events flow through, they'll displace the old ones, and then every second or so it'll emit a list of what it knows about the universe. We need to compose these things together. We've already seen the straightforward chaining. If I say rate 5 graphite index, I'm going to obviously take a rate every 5 seconds, and I'll send it to graphite and I'll index it. But what do you mean by send to both? Well, in Riemann, all events are immutable. So it actually kind of like pulls them apart. You get a copy, one for each stream. So this means that index and graphite are going to see the same event. And because they're immutable, one of them can't screw up the other. When you make a change in Riemann, when you use with or adjust or whatever, it actually makes a new copy of the event with different parameters and sends that downstream, which means that you don't have to worry about streams interfering with each other. They can compose freely. So we split things and send downstream. And I said index. The index in Riemann is like a big coalesce. It's the sort of sink to our water table. All streams typically flow into the index at some point. And when they arrive, they are ordered by host and service. Again, these are the primary spatial keys. And so you could think of a new event for API 6 arriving, kind of stacking on top of the old one and pushing it, glugging down into the water. And what's at the surface of the water, this is our picture of the current state. This is saying, okay, here's what we know about API 6 and API 7. We don't know what's going on in API 8. It's sunk, its TTL is expired, it's fallen into the depths. So what do? We used to know about API 8, but we don't anymore. So Riemann will emit a ghost. I am the ghost of Nginx on API 8, fear me. So that ghost will float up, and this is, you ever see those like children's textbooks where they show you the carbon cycles? Anyway. This is the expired cycle for Riemann. They flow back to the source of streams, and this time they have state expired, and it tells you we no longer know what's going on. This is how you detect transitions without necessarily needing something to push to you. Right? So people often say, oh, without a polar, how do I know a service is gone? You know it's gone because it failed to check in. So we can explicitly filter to expired events and warn those are lost. We could extract a change in state and then page an operator about it. And in fact, that change state operation, that's just holding on to the current state and comparing it to the new state. Now, if we did that across every event that came through, we'd be comparing events from different hosts and services. So like API 1 could be okay, but 2 could be critical, and it's going to flip-flop back and forth between those two and think that it's seeing changes all the time. That's bad. Right, we wanted to have a separate change, a separate state to be tracked for each host and service. So we'll wrap up that change state in this operator called by, which says for each unique host and service pair, give me a copy of the stream below. Now, because this is a list and we have macros, by actually does not evaluate change state. It interrupts evaluation, it saves that code, and evaluates it later at runtime to generate new streams, one for each host and service. So as API 1 shows up, it'll run that code and build us a new change state. And as API 2 shows up, it'll build a new change state for that. And API 3 shows up, we get a new change state for that. So everybody has an independent state, and they recombine to pitch the operator. Recombination is a little tricky, right? Like when you represent code in a tree, how do you repeat the same thing at multiple levels? Like trees are defined by not coming back together. So we need a way to represent that. We do it with variables. So if I say let the index be this index call and let graph be some graphite call, index and graph, these are lexical variables that are scoped inside the let binding. And every time I refer to them in the streams, it's the same stream, it's the same variable, so it points back. So pointers, references, this is how we achieve unification. And we can also do anonymous unification. So let's say I wanted to have a manifold, without giving it a name, I want to split things up and then bring them together. Split them up, bring them back together. So pipe says, give me a symbol, let's call it down arrow. That represents the next stage of the pipeline. And then I'll do the split, I'll compare a metric. Where the metric is greater than 0.9, I'll assign state critical and then pipe down. When the metric is greater than 0.5, assign state warning, pipe down. Otherwise, call it okay, pipe down. Those 3 down arrows, they all point to the next stage of the pipeline, which is that change state scheme. So this code lets us take unstateful variables. They have no state in the events. They have a metric. We can split them up, look at the metric of each one, assign a state, and then recombine the states in the same changed analysis so we can extract state transitions. It's not enough to work independently. We have to play well with others. Riemann has integration for a whole bunch of services, and it's easy to write your own. Since streams are just functions of events, if you can write a function, or if you can write a Java interface, you can write yourself an adapter. We talked to, notably, Boundary, Datadog, Graphite, and Librado for time series, OpenTSDB, and Influx, especially there. We can also port things into your Slack channel, into your HIP chat, and of course we can page people via everybody's favorite PagerDuty. A lot of services send data to Graphite as well, or send data to Riemann. You do application metrics from your actual app using any number of clients in various languages. Riemann tools gives you small daemons that run and monitor like MySQL or node health. Collecti, Nagios, Statsy, Graphite, they can all push data to Riemann as well. And you can do sort of language-specific things. JMX can port us data too. Of course, Riemann nodes can communicate with each other. If you establish a forwarding stream, it acts as a stream that just pumps everything over TCP to some other service. So you can link together Riemanns in a hierarchy, aggregating at progressively less temporal resolution or less spatial resolution as you go up. And with that additional complexity, we need some ways to organize it, to control it. I hope this is becoming clear. These are not just configuration files necessarily. They're full programs. Like when I was writing Nagios configs, I ended up writing all these like scripts to emit Nagios configs, and then scripts to emit scripts that emit Nagios configs. Like you build your way up the abstraction layer because the language bottoms out so low. And this happens in Twitter's observability platform too. Like they've got a very simple configuration language. People write macros on top of it. People write scripting languages for APIs to do monitoring. So I wanted to have a programming language which is a first-class citizen. So we have function definitions that can construct new streams, and we can organize those functions into namespaces. So all of the code organization tools from Clojure are available natively here. And this extends to being able to pull in arbitrary JVM code or other libraries from the net. You can tell Riemann, hey, grab me this Maven jar, and it will like suck it in, and you can make calls to your own Java, whatever it is. This is really handy for building esoteric, weird monitoring stuff, because we all have one-offs. Of course, this complexity brings with it software. Software requires testing. We have this IO stream, which says only in tests, don't do anything below me. Just intercept it, throw away. So you can wrap the operations that would normally send you email or would normally page somebody. You can wrap those in I/O and they won't run in your tests. And you can add a tap, like say tap graphite, and then we'll do some I/O and graph it. That tap, only in testing mode, records everything that comes through it. You can ask later and say, hey, what did this tap see? And you can use that to make assertions about your configuration. So, general learnings. We have 4 protocols. You can speak TCP, UDP, HTTP, or graphite. TCP is ideal. It speaks protocol buffers. It is very well optimized. UDP, do not use this in any monitoring system ever. People love all that is holy. UDP has no flow control. UDP has no back pressure. You have to build these things on top of it. And if I built them for you, your client would be responsible for maintaining the state machine necessary to do its own flow control. We would call it TCP. I'm being somewhat facetious, but the gist of this is that UDP, even on local hosts, like hi statsd, even on local hosts, the kernel buffer is free to just say, what do you mean those packets? Like, it will just drop them on the floor. When you bring too many groceries home, you're like, screw it, and throw it down the stairs. Maybe you don't do that. So there's also an HTTP protocol. HTTP is a good fallback when you can't speak the protocol buffer's implementation because it's just JSON. Everybody loves JSON, everybody loves HTTP. It is slow. By slow, I mean about 10 times slower than TCP, which means somewhere in the order of like 1 million events per second instead of 10 million, depending on how you encode it and how you batch it. Your mileage will vary. We'll talk about that. There's a graphite plugin because what doesn't speak graphite? Graphite is a very limited subset of the Riemann event model, so you're stuck trying to extract information back out of that. You'll have to write parsers to really regenerate a full schema out of those events, but it's possible. Use the testing. Use the hot config reloading. You can actually tell Riemann, hit it with a sig hup, and it will reload its config, generate new streams, and start applying events to them without breaking TCP connections. This is really nice for doing low downtime changes in your config. Riemann commits one of the many cardinal sins of distributed computing. We assume clocks are uniform and synchronous, and monotonic for that matter. These are terrible assumptions. Why would you ever build a system like this? Oh, that's me, right? So, this is like pragmatically, it's an okay thing to do some of the time, but it will mess you up. If your clocks are not synchronized, it'll manifest as weird anomalies, and it's hard to explain why. I want to fix this. I can't yet. So, instrument your clocks view. Riemann is a transient system explicitly. We give no disk persistence, which A is good for performance, but B, your state gets recreated from scratch every time you do a failover, every time you restart. So in Riemann, any state in the streams should be trivially recreatable within a couple of seconds. And if you need information about definitely page me this thing never shows up at all, that has to be encoded into your config because it always has to be encoded into the config somewhere. Riemann is not a distributed system in the sense that you might think. It does not do sharding, it does not do failover, there's no clustering of any kind. It's a single node, you just hammer it with stuff. You can throw, CoreSync or Heartbeater or Linux HA in front of it. That works, that gets you most of the way. I wish I could do better. The trade-offs are incredibly complicated for building an AP monitoring system. I have no idea how to do it. There's a couple research papers though. Riemann, if you are a Rubyist, may be slightly faster than you used to. I ran Nagios polling for a long time and Cacti, and it was used to being like, okay, I made a change. In 5 minutes, I'll know. I'll see 1 pixel on my graph if it changed or not. Riemann's latencies from change to web browser are on the order of 20 to 30 milliseconds. It's wonderful to be able to hit the enter key on a shell and then see the graph change immediately. And of course, if you do a 5-second roll, you have a 5-second latency. But having this low boundary means you can react, you can orient, decide, and make your decisions quicker. And also, we emphasize being able to push a lot of data through Riemann at once. Because it's transient, because it's single node, because we do no sort of coordination, you can pump 1 to 10 million events per second through it on decent hardware. Maybe. We do arbitrary computation under the stream set. So if your function is expensive, no, it won't be fast anymore. So in practice, anywhere from 10,000 to a few million events per second per node, depending on CPUs, depending on virtualization, depending on workload. We have TLS, bidirectional authentication. This is the Riemann answer for where's the password? No, you do assert, you sign on both sides, you verify both sides. I'm probably doing it wrong because the Java crypto APIs are terrifying. Riemann provides back pressure. This is a thing that most people who are writing clients in any sort of monitoring system get wrong. it's going to give you an acknowledgement message that says, hey, I'm done with this thing. So if you're just blindly sending events into Riemann, or blindly sending events to any downstream service anywhere, at some point, it's going to get slow, or it's going to go unavailable, and your TCP queue will fill up. And then the client's TCP queue will fill up, and then the client stops doing work. This might be good. Maybe you want to propagate that back pressure all the way back down the chain to some other client. Maybe you start returning 503s. Maybe instead you load shed. You start dropping messages on the floor. But it's important to have control over that. Riemann does not do load shedding by default because it wants to give you the power to choose whether you want to do load shedding. So, do your sends asynchronously. Don't fire off network requests in line with your application code. You update a variable, you update a queue, and then some background thread is relaying that information to Riemann. And moreover, it's not just doing like a send, wait for receive, come back. You can if it's slow, but if you're sending a lot of events, you want to be pipelining. So you'll have maybe 1,000 events on the wire that are flowing across, and you're accounting for latency in the queues at both ends. And then you try to keep that number somewhere around 1,000 depending on the acknowledgements. There's a little state machine you can build around that. So, to review, Riemann is a fast, transient, marketplace, clearinghouse, sort of commons area for distributed systems visibility. Things like application latencies, signups, node health, CPU, database stats, downstream services, all this stuff unified, from business PKIs to single node application metrics. Events aim to unify the representations from a lot of different monitoring systems that I've used in the past and bring them together in one scope so we can talk about them in a shared language. You can think of it like public transit. You know, I'm an application, I just want to go out of my house and get on a bus and wind up somewhere without having to worry about the 10 different modes I'm going to have to use. I have one ticket, one protocol, gets me everywhere. So a client only has to speak the Riemann protocol, only talks to one thing, and then when I need to switch from Graphite to Influx, or when I need to add some side channel monitoring platform, when I need to do additional instrumentation, I don't have to deploy 80 different distributed systems with this monitoring change. I can make the change in the config in Riemann, and then it can do the routing for me. We can do this with a powerful stream language for complex transformations, and the worst UI ever encountered by human client. I'm so sorry, I am not a JavaScript engineer. Ultimately, Riemann is a system built for weird people like me. I built this because I was experiencing great pain. And I built it in this sort of uncompromising way that I'm going to build this weird thing, I don't care what anybody thinks, and let's see where it winds up. And a lot of these ideas around low latency, push, rich events as maps, stream processing languages, code as configuration, these have started to crop up in other monitoring systems. So over time, I think these ideas in Riemann will become less unique, and we can all reap some of their benefits, hopefully in a way that's saner than what I built. Even though it's weird, I hope it might be useful for you too. People at The Guardian, people at New York Times have wound up using it, a bunch of financial services firms. I am shocked and alarmed and kind of delighted. This is Riemann. Thank you very much.